So I have a presentation about some findings or some results we have obtained in WP3 about the work done to mimic and to continue the work done by Raillard et al. To propose a Monte Carlo simulation approach to estimate extreme wind speed. So we'll go into details. So as everyone knows here, the typhoons or hurricanes or tropical cyclones are events that are scarce by nature. And if we take here an example of the historical database that we have, if we want to estimate wind speed at a given location, so I've taken the location studied by Ishihara and Imaguchi, which is a location in Japan. If you take the historical data that is available on a recent period, so taken here from the NOAA website, we have 63 events at a distance of 500 kilometers, which is not that much if we want to estimate events with very low probability. Furthermore, we do not have direct historical measurements, so it is the work that has been done within the project. How can we derive historical winds without direct measurements? So we relied on a parametric model, parametric wind model that gives the surface wind speed given the parameters of the tropical cyclone. So for example, here I have taken one specific event, the one that leads to the most important wind at the location, which is Faxai. So at the closest location here that I have highlighted in this screenshot of the website, of the NOAA website, we can have the parameter of the tropical cyclone. And then using the work that has been done by the colleagues from Ifremer and France Énergie Marine, we are able to derive the corresponding wind speed using the parametric model at a specific location for this situation. So on the bottom left here, you have an example of what has been implemented into the web application developed using R and Shiny that allows to play along with the different parameters. So we have sliders here that allows, it's not interactive here, but if you change the radius of maximum wind speed, for example, then here you can have an estimation of the wind speed of the spatial pattern of the wind. And of course, you can use this model to compute the wind speed at the given location. So it allows to compute the wind speed from the parameters of the tropical cyclones. So what is done classically is to rely on the GPD or peak threshold approach. So you select a threshold, and for the values that are above this threshold, you choose a specific distribution that is called the generalized Pareto distribution. And then you have several techniques to estimate the parameters of the model, and then to estimate the return levels from this model. Of course, there are large uncertainties that are associated to this method due to the paucity of data. So I have an example here on this figure. So you have to choose a threshold. Here you have the best threshold is the minimum wind speed that we observe in the data, which is subject to discussion always. And you have an estimation of the wind speed up to 500 years return level. And we have a very large uncertainties, which is just the parametric uncertainties that are linked to the fact that we have not many data to estimate. So what is done classically as the work that we are based on is to augment the historical database using a technique that is called the stochastic weather generators approach, meaning that we will rely on an accurate description of the past events and a method to enhance this database, to augment by a cheap simulation that will be allowed to generate possible events, generate as many events as we want of the possible events, synthetic events, stochastic events, of synthetic tropical cyclones that will be described by the parameters that we used previously. Which is called a Monte Carlo approach, because we rely this approach on generating many independent tropical cyclones. I will describe in the cycle the two elements of this method, which is the marginal distribution of the parameters and the joint distribution of them. So on the left of this slide, you have an example of the historical data that we have at a specific location. So tropical cyclones will be defined by 7 parameters. So the wind speed, the direction of the cyclone, the maximum wind speed, the distance between the cyclone and the location, the bearing, the angle of sight between the point and the cyclone, the difference of pressure between the ambient pressure and the center of the cyclone, and the radius here of 34 knots. So we have the historical data here on the left side, and the scatter diagram and the correlation on the two upper and lower triangles. So for each variable, we need to fit a model, a distribution that will mimic the distribution that we see here on the diagonal. So we have two kinds of distributions. We have unbounded distribution, positive distributions for speed, for example, for wind speed, for the pressure. So we tried a large number of different distributions here that are indicated here, with different number of parameters, and also the mixtures of those distributions. And the model selection has been done using the IIC criterion. And we also used specific distributions to model the bounded distributions that allow to model, for example, the bearing, the distance, things like that. And we also have specific distributions for the directional variables that allows to have a proper statistical distribution of the parameters. Using this the fitted distribution, we can transform to uniform margins, and then we will model here. All the distributions have the same, all the parameters have the same distribution, and then we can use classical statistical models that are called copula, that allows to model here the distribution. So here, the way the points are distributed into on the space 0,1.01. So we tried several models. So the classical normal copula is used by previous work, and two statistical methods more recent, the beta empirical copula, that is a fully non-parametric method, and the regular Vine copula, which is a parametric approach, a simplified approach to model a large number of the dependence within the large number of parameters. And the idea was to keep models that are easy to fit and that are cheap to simulate. So for example, here I generated 10,000 points on the right of the plot that are intended to mimic what we have on the left plot. So I shown here the correlation and the contours. The contours to be very density between the points. So if you compare, for example, the wind speed here and the pressure, you see that the two are very well correlated, what we see in the data. And the beta empirical copula allows to catch here this dependence. But it can also catch more complex dependence here, for example, this one, which is here, which is much more complex to model, but is well catched by the model, the empirical beta. So using this, we can generate, as I said, a large number of different examples, and we can compute the return levels based on this Monte Carlo simulation. So I compare here the 3 different dependence models. We can see that it do not have very it is not as important as modeling the marginal parameters. I do not show it here. But we can also see that this method replicates the historical wind. can provide estimates for annual return period, as long as we simulate enough synthetic tropical cyclones. And we also estimated the uncertainties by using parametric bootstrap, meaning that we fit the model a large number of times on the simulated data to estimate here confidence interval. And we can also provide the direction of each cyclone, which is represented here on the right for the different models. The red dots are the historical data, and we can simulate here a large number of events and estimate the dependence between the wind intensity and the wind direction, which could be used also to incorporate, as Jean-François said, effects on the surface wind speed, such as the orographic or land effect, speed up ratio, for example, depending on the surface, which will depend on the direction and the position of the cyclone. So to conclude on this approach, we have a very versatile tool and very easy to use and to simulate. So it has been implemented into a web application. Jean-François already told about that has been developed using R and the Shiny package. And it has been proven to be a very robust and versatile method. So we tried to apply this method not only to the historical location I've shown here in Japan, but also to different climatologies. For example, in New York, in Taiwan, or in the French island of Mayotte, which allows to estimate here very different climatologies, very different historical data. And also, we see that when we have a few number of events, such as in Mayotte, we also reflect the non-confidence that we have into these historical data. So on the right-hand side here, I mean, we'll finish with that, is just an example of the web page that has been developed within the RS Shiny package that allows to present the different the marginal models, the joint models, and the estimation of the wind using the different models.